Hey everyone, Ricardo here, and in this video I'm going to be showing you how to set up a line current differential scheme using the SEL-411L protective relay. So a line current differential scheme is very similar to other types of current differential schemes where we're comparing the current entering and the current leaving a protected zone and declaring a trip if there's a discrepancy between these two currents. Now in the case of a line current differential scheme is a little bit different than a transformer or a bus differential scheme because the two ends of the protected zone are far apart. So in this case we use different relays at the ends of the transmission lines, and then these relays communicate with each other via fiber. This way they can send information to each other as far as the current measurements at each end of the transmission line. Now before we go deeper into how to set up the line current differential scheme using the SEL-411L relay, make sure to subscribe to the channel. We will post videos here about power engineering and power system protection and control. And if you want to learn more about power system protection and control, check out our online courses on our website where we go into these topics in a lot more detail. I'll leave a link to those courses in the description below. All right, so let's get right into it. Let's see how we can set up a line current differential scheme using the SEL-411L protective relay. So let's say, for example, that we wanted to implement a line current differential scheme for this top transmission line that I have over here on the screen, which I've called T line 1. So this one over here. And in this case, we'll be using two SEL-411L relays, one at each end of the transmission line. So we have one over here on the left side and one over here on the right side. Now, as I mentioned before, the whole concept here is that these relays are going to measure the currents at each end of the transmission line, and they're going to send the information regarding the current measurement to each other via a fiber communications link. And this is, of course, so that they can determine whether there's a fault inside of the transmission line or not. So again, this is similar to a bus or a transformer differential scheme where we have a zone of protection for which we're measuring the currents and comparing them to see if there's a discrepancy between the two. So in this case, of course, the zone of protection is our transmission line, and we're going to measure the currents at both terminals, the one at substation T sub 1 and the one at substation T sub 2. Now, unlike the bus or the transformer differential scheme, in this case, these relays could be very far apart. So the comparison cannot be done fully just using the CTs and wiring them to one relay. Here, of course, we have to have two relays, one at each end of the transmission line, which then send the current information to each other. So for example, in this case, if I open this transmission line model, you can see that the length of this transmission line is 5 miles, which is roughly 8 kilometers. So of course, we cannot just use one relay and have CT leads that are 5 miles or 8 kilometers long. All right, so again, I'm going to talk about more specifically how the SEL-411L relay does this current comparison later in this video. But let's say, for example, that we had two cases here. First, let's say that we had a fault that is external to the transmission line and it's at T sub 2, so the substation on the right. So let me go ahead and place a three-phase fault on this substation on the right. And in this case, we see that the current at terminal TL1_1, so this terminal over here, and terminal TL1_2, this one over here on the right, the currents at both terminals is exactly the same. In other words, the current that enters the transmission line on one side, in this case on the left side, is going to exit on the other side, again in this case on the right side. So this is what we call a through fault. So both CTs see the fault current, but it flows through the transmission line and into the substation bus at T sub 2. So it is external to our zone of protection. And of course, this would also be true for normal load conditions where we have a load, let's say on the substation on the right, we would see the current flowing through the transmission line. So into the transmission line on one side and out of the transmission line on the other side. And again, this flow of the current is expected since the fault is outside of the protected zone. Now, to take this a little bit further, essentially what we're saying is that what the relay defines as the differential current, that is the difference of all currents entering and leaving our differential zone, which in this case is the transmission line, is going to be 0 for this case. And again, this is because it's an external fault. So the differential current is going to be 0. And let's actually go ahead and do the math for this real quick. Now, to calculate the differential current, we have to add the currents on both sides of the transmission line. So in our example, we have, and let me actually go ahead and draw it over here. We had T sub 1 here on the left, and we had T sub 2 over here on the right. And we said that for this example, the fault was external to the transmission line at T sub 2. And we also said that the fault current was 2314 at an angle of minus 83.9 degrees. That is flowing this way. And we also have on the other side the exact same current, 2314 angle minus 83.9. And this, of course, is amps and amps over here. So what we can do over here is just add up the two currents together to calculate the differential current. So I'm going to define IDIF as the addition of those two currents. So I have 2314 angle minus 83.9, and then plus 2314 at an angle of minus 83.9. And here I'm going to subtract 180 degrees. And I'll explain here in a second why. So if I calculate this, of course, I'm going to get just 0 amps at 0 degrees, meaning that there's no differential current. Now, the reason why I subtracted 180 degrees from the TL1_2 terminal is because the current on that terminal is exiting the transmission line and is flowing out of the polarity of the CT. So in other words, if we look back at the ETAP model, I can see over here that I have this current 2314 angle minus 83.9, but it is flowing out of the polarity of this CT over here on the right, while the current on the left terminal is flowing into the polarity of the CT. So I'm going to define this current as positive on the left side and as negative on the right side. That's an important point. We always need to take a look at the CT polarities and how the current is flowing. And again, that's the reason why I subtracted 180 degrees here from the T sub 2 current. So again, we can see here that we get 0 amps for the differential current. And of course, that's expected for an external fault. Essentially, we're saying that the differential current is 0. And this would also be the case for just load current that is flowing through the transmission line. So in on one side and out on the other side. Now, coming back over here to the ETAP model, let's say that now we have a fault inside of the transmission line. So I'm going to change this fault and I'm going to place it right here inside of the transmission line on the T sub 2 side. Now notice here that the current magnitudes are different from both sides. Here on the left we have 2314 amps, while over here on the right, it's a little faded, but it's right here, we have 7314 amps. And the currents are entering the transmission line from both sides, so they're flowing into the polarity marks on both CTs for both sides. So I'm not going to subtract or add 180 degrees for the current angle. I'm just simply going to add up these two numbers to get the differential current. So let's go ahead and do that. Let's go back over here. And this, of course, was for an external fault. And so now let's do the internal fault case. And same thing, let me draw our model over here. So I have T sub 1, transmission line, T sub 2. In this case, our fault is inside of a transmission line. And I have from this side 2314 angle minus 83.9 degrees. And from this side, I have 7314 angle minus 84.2 degrees. So now if I add up these two currents, I get that the differential current for an internal fault is going to be 9627.98 at an angle of minus 84.13 degrees. And again, all I did here was add up these two numbers over here. And again, I said this before, but remember that we have to take a look at the CT polarities. This is important. And for example, in this case, both currents are flowing into the transmission line and both CT polarities are looking into the transmission line. So that's why I have taken both currents here as positive. And so we can clearly see that for an external fault, so the first case that we looked at over here, the differential current will be 0. And again, this is also true for load current. But for an internal fault, the one that I have over here, the fault current will be usually very large, and the magnitude of internal fault differential current will depend on the sources at each end of the transmission line. So this number will vary. It just depends on how strong the sources are at the two ends of the transmission lines. Now, one more point that I'll make over here before we move on to the instruction manual is that there are always errors in the current measurements. So for an external fault, the differential current won't exactly be 0. So I know that on here we calculated 0, but that's just assuming that everything works perfectly. There's no errors on the CTs, there's no relay measurement errors, there's no communications errors, etc. In reality, of course, this is not going to be exactly 0, but it should be fairly close to 0. And then for an internal fault, again, this is the ideal case where we're perfectly measuring everything, but this will vary a little bit. There's always going to be some error that is introduced by CT measurement errors, by the relay measurement errors, by just errors from the communications. So I just wanted to point that out. These numbers are for the ideal case, but of course there's always going to be some errors, And this is especially important for the external fault where we know that the current won't exactly be 0. All right, so now let's move on to more details on the SEL-411L relay. Let's take a look at the instruction manual. And so what I have over here is just the instruction manual for the SEL-411L relay. And in here, I want to go to page 167. And this page number, of course, varies depending on the revision of the instruction manual that you're looking at. But what I want to show you here is this picture over here. And so basically the concept that I just went through is on this image over here. Here you can see that the relay defines the differential current, this one over here, as the summation of all the currents from the CTs around the protected zone. So in our case, for example, we looked at a 2-terminal transmission line with a straight bus configuration on either side, but it doesn't have to be just one CT at each terminal, or even a 2-terminal transmission line. It could also be a 3-terminal transmission line, for example. Now, if you look at this example that we have over here, you can see that we have either a double bus, double breaker configuration or a breaker and a half configuration at any of the 3 terminals. And so also notice here that we have 3 terminals and not 2 terminals. So we have 2 breakers and 2 CTs for each terminal, and then this is a 3-terminal line. Now the same holds true though. All the currents are summed up, and that is what is defined as the differential current. And again, you can see that over here on this equation where they're saying that the differential current is the summation of the local current and the remote current number 1, remote number 2, and that of course is equal to all the CT currents added together. Now the other important point you can see over here is that we of course are going to have just one SEL-411L at each terminal. And so each relay is first summing the 2 local CT currents, and then the combined local current is what is being sent to the other relays. So basically what I'm saying is that, let me actually get rid of this first. What I'm saying is that we're going to have an SEL-411L relay over here. This CT and this CT is going to be wired to that relay. And then we're going to do the same at the other 2 terminals. So we're going to have an SEL-411L here. This CT is going to be wired to that relay. This CT is also going to be wired to that relay. And we're going to have a last one over here at the 3rd terminal. Again, this CT and this CT is going to be wired into that relay. And so what each relay is doing is it's first summing the 2 local CT currents and then sending the combined current to the other 2 relays in the scheme. And this is just for efficiency in the communications link. So you only send one value for the current at each terminal. But for the purposes of calculating the differential current, the main point is that it is the summation of all the currents from all the CTs covering the protected zone, which in our case is the transmission line. Now this defines the differential current, and the relay uses this current to provide a threshold for which the differential element is allowed to trip, as we'll see here in a second. However, we must also define a characteristic for the relay to distinguish between internal and external faults that provides security during non-ideal conditions. Again, I mentioned this before, but we're always going to have CT errors, relay errors, synchronization errors between the relays, etc. So the characteristic that the SEL-411L relay uses is actually on page 169 of this version of the instruction manual. And it's this one over here, which is called the alpha plane. Now, this operating characteristic defines when the relay is allowed to trip or not based on the ratio between the local current and the remote current. Now, each relay is independently performing this calculation and declaring a trip or not. And it does this based on its own local current measurement, as well as the remote current measurements it receives from the other ends of the transmission line. And again, this characteristic provides good security against errors. Now, let's run through the 2 examples that we looked at earlier for an internal and an external fault. And here we're going to take a look at the relay TL1_1, so the relay on the left side or the left terminal. But remember that each relay is doing its own calculation independently. So again, going back here to the external fault case, and let me actually move this down a little bit so we have more room. If we look at the external fault case, so the one that I have over here, again, this calculation is applicable to relay TL1_1, which is the relay on the left terminal in our example. And K, the phasor K, is defined as the local current divided by the remote current And of course here, local or remote depends on which relay we're looking at. In this example, we're looking at the relay on the left side. So if I calculate this phasor K, I'm gonna get 2314 angle minus 83.9 degrees divided by 2314 at an angle of minus 263.9 degrees. And this comes from this right here. So minus 83.9 minus 180 gives me this angle over here. And so if I calculate this, I get that this is equal to 1 at an angle of 180. And again, this is for the external fault case. And this, by the way, is the ideal case, again, for an external fault. The phasor K will be at 1 per unit at 180 degrees. And again, this is a perfect case neglecting errors. In reality, this won't exactly be 1 per unit or at 180 degrees, but it should be fairly close to that. Now, for the internal fault case, if we go down here, we can do the same thing. We can calculate the phasor K as the same thing. So I local divided by I remote, which in this case, for the internal fault case is 2314 angle minus 83.9 degrees divided by I remote, which is 7314 angle minus 84.2 degrees. And so if I calculate this, I get that this is equal to 0.316 angle 0.3 degrees. Now, looking back at the alpha plane, again, what we did here is we calculated this phasor K, and then that's going to tell us where on the alpha plane we are. And so this region on the left side is defined as a restraint region, so we don't trip if our calculation is in this region. And this region on the right side is the operate region. So going back to our example, we calculated for the external fault case 1 per unit at 180 degrees, so this number over here. And for the internal case, we calculated 0.3 per unit at 0.3 degrees. So going back to the alpha plane, we can say that the external fault case was right here, 1 at 180 degrees. And the internal fault case was somewhere around here. We calculated that to be 0.3 at roughly 0.3 degrees. And again, the external fault calculation, this one falls in the restraint region, so we won't trip for that case. And the internal fault case falls here in the operate region, so we will declare a trip for that case. Now, to take a look at when the relay declares a trip, we have to take a look at the internal logic of the relay. And that is on page 197. And that is this logic that I have over here on the screen. And remember that I mentioned this before, but for the relay to declare a trip, we must have two conditions. The first one that we looked at, which is on this part of the internal logic, which then feeds into this top part of this AND gate. And this is the threshold of the differential current. In other words, this right here is the calculated differential current, which we calculated before, and that has to be above some threshold that we define via settings, which is this setting over here, 87 LPP. So this portion of the AND gate is basically saying, do we have enough differential current to declare a trip? Are we seeing an internal fault based on our calculation of the differential current? Now, the other condition that we have to meet is this bottom part of the AND gate, which is essentially saying, is the K phasor that we calculated, basically the ratio between the local current and the remote current, is that phasor in the operate region of the alpha plane? So two things have to be true for the relay to declare a trip, which ultimately comes from this relay orbit over here. We have to have enough differential current, and the K phasor, the ratio between the local and the remote current, has to be in the operate region of the alpha plane. And then of course we can use this relay orbit in our trip equation to declare a trip. So we would program that relay orbit into the trip equation, then we would program the trip equation into a contact applet that then goes and hits the trip coil of the breaker. Alright, so that's how you set up a line current differential scheme using the SEL-411L protective relay. If you want to learn more about power system protection and control, check out our online courses on our website where we go into these topics in a lot more detail. We have online courses on transformer differential protection, bus differential protection, protective relay logic, and much more. And as always, make sure to like the video if you found it helpful and subscribe to the channel for more videos about power engineering and power system protection and control, and we'll see you in the next one.